So for the last subject with regards to collisions this week, we're going to talk about the separation axis theorem, or separating axis theorem. I don't know. I've never quite found two articles or two books that say it the same way. I guess there's only two, so if I have more than two. Anyways, either way, separating axis theorem ultimately is a very simple idea, which is if I can somehow draw a line or take a plane and somehow put it between two objects where neither object is touching that plane, then I can assume that they're not touching. So separation axis theorem is a really fun, eloquent little theorem that allows us to have this early out approach to determining the collision of two objects by determining, can I, like, imagine like a piece of paper, if there's two things in the air and I put a piece of paper between them, well, and then the paper doesn't touch either one, then they're not touching each other either, right? So this is sort of a really cool little test that allows us to determine if two objects are, overlapping in any substantial way, given that they occupy a particular, if they share a particular plane or not. So it's a really cool idea, and works extremely well. So let's go back to this example here. When we have our axis realigned bounding boxes, we can see that our axis realigned bounding boxes are overlapping. We detect a collision, but the objects themselves are not actually touching, as we know. Think about that idea, what I just mentioned. Imagine a piece of paper. Can we insert a piece of paper between these two objects? And we obviously can. There's a big space between them. We can park a fire truck in there if we wanted. So now we take the same idea with a bounding box pretest, and even though this doesn't register a collision, and so this is one way to approach it, obviously, but you can still see that the bounding volume hierarchy, the axis realigned bounding boxes are still overlapping. Yet right now, if we were to imagine the pretest with something much closer, it would register even though there's technically no overlapping with the two. So to overcome this, what we really want is we want to be able to test the oriented bounding boxes against each other. So those white boxes here, which are originally our axis aligned bounding box that we then rotated in space, we want to be able to test those against each other. For example, in this case, both the sphere would detect a collision and the axis realigned bounding boxes would detect a collision, but we can see there's no collision, right? There's a very small little point here. I mean, obviously, if we saw this in 3D, we could kind of see much better, but in 2D, we can see that there's a small little sliver here where if I drew a ray from the camera, I could draw it between the two without touching either. And so the separation axis theorem ultimately lets us determine if there is a collision by checking all these different planes and seeing, is there a collision between this plane or that plane or the other plane, and so on. And the way we do that is quite interesting. So you can kind of imagine, you can kind of see here, these two objects are colliding because they're in each other's space. The bounding volume hierarchy, the oriented bounding box of each one is overlapping. Now, again, this particular example demonstrates the limitations even of oriented bounding boxes. Like, what do you do? How do we win this game? We can't seem to get these two objects to perfectly collide. However, now in this case, the error is very, very much smaller. And just to kind of give you a hint, how do you resolve the situation like this? Well, you would use a hierarchy of bounding volumes. At a certain point, you start to have to get a little bit more complex or think about it with compositional mentality, because at a certain point our simplifications of bounding volumes do break down. But here, this is about as good as we can get with an oriented bounding box without going the next step, which is going down to the mesh level or going down to multiple volume hierarchies. So what is the separation axis theorem all about? Like I mentioned, imagine having a plane somehow that we can stick between them, and if we can and if they're not touching them, then they're not touching each other either. So this plane is clearly, we can clearly put this plane in there. They don't touch either. But what happens when we do have a situation where the two are touching the same plane? So in this case, you can kind of see, I think the idea here is that the bottom model is just barely touching that plane, and the top model is also just barely touching that plane. This is like sort of a plane where they touch on a particular axis. But we can clearly see that there's another plane we could use instead of this one. So this one they may be touching, but there's another plane that's a diagonal that we could have sliced kind of between them. And so the separation axis theorem for different kinds of geometries allows you to test about, I think it's 15 different tests, 15 different planes that you can check against each other, and we'll talk about those in just a minute. So as you can kind of see here, here's another plane where the two are clearly not touching. Yeah. Yeah. So generally speaking, to do the SAT, what we do is we take a given model, we take a given plane, and then we actually project the models onto that plane. So as you can kind of see here, there is this particular axis. You do have an intersection. I think that my slides are misformatted, but if you can kind of imagine the left object being projected onto that plane, and then the right and the bottom object being projected on, like flattened, you know, like a little line and a little line, there'd be a little overlap. And that's, I think, the key is separation axis theorem. You want to take one object and you want to project it onto a plane. You want to take the other object and project it onto the other plane. And you do this for a bunch of different axes. Like, so here we have a small overlap between the two. Here we have another small overlap, right? The top object would collapse down to a little flat, and the right object would collapse up into another flat, and you see there's a little bit of overlap between the two. However, there's a plane, there's an axis we can clearly see where the two don't overlap, and that's this axis. So we take the axis of Steve, the y-axis of Steve, and if we were to project the two objects onto them, actually no, that's, am I not explaining this particularly well? No, in this case we would also have an overlap of the two. So we this is not the case. This is not the axis. I'm thinking about this in the wrong way. The axis that we want to draw. So this is something I guess I have had trouble too with understanding. The axis and the plane you want to draw are kind of like they're perpendicular to one another. So in this case, we're projecting these two objects onto each other, onto this plane, onto this axis, and in this case, they're very much overlapping. They're like pretty much perfectly overlapping on the axis of y of Steve. However, if you look at an axis that's not drawn here, which is the x-axis of Steve, which this one, the red axis of Steve, right? If you drew a line from his feet up in the direction of the left and the right, and you squash those down, they would not be overlapping, and that would be your failed separation axis test. And so you can kind of see, apologies about the loop-de-loop there, but ultimately you're taking every axis of the given object, so x, y, z, check each one of those. The other object, x, y, z, check those. So now you've got 6 tests, just like you did with the axis-aligned bounding box. And then you have to take the cross product of each respective one as well. So you can kind of have this x with this x and this x with this y and so on until you get, and you'll have actually a total of 15 tests, an additional 9, so 3 times 3. And so in the case of, so to simplify the test, we can use just squares. But for the most part, like it kind of, the math kind of turns out the same way. If you want to, you can do this with other shapes. You can do this with hexagons. You can do this with triangles even. But like you can even do this, by the way, with really complex geometry, like parametric surfaces and things like that. And I'll post a link that is a very, very good article about this subject, and it shows a lot of kind of these interactive JavaScript widgets that you can play around and just see how things kind of project onto these planes, onto these axes. So if we think about 2D, 2D is pretty easy. We have the X and the Y, and then and that's it, right? Each one has their respective X and Y, and that's it. There are no other 3D. If you took you can't get another thing. You can't cross them because you'd get into the Z, and that's not something that we're doing in 2D. So in 2D, the separation axis theorem is quite simple, and is usually what's used to explain this mathematically. But with 3D, we have to do not just the X, Y, and Z of each respective bounding box, but also the cross product of all the combinations. And you're saying to yourself, wait a minute, that's a lot of calculation. But again, think about early out. Most of the time, you don't even get to this point. Most of the time, you had an early out either in the bounding sphere, or you did you did the axis aligned and it failed, and then or eventually you get through this and one of these tests fail early on. So yeah, it's not actually a lot of work. Let's take a quick. These do not seem to work. And this is not a valid URL. Here. So let's check this out.
I'm going to explain to you the separating axis theorem, also known as SAT. The separating axis theorem is used to check whether or not two objects are colliding. For this explanation, I'm going to use two cubes. We want to check if cube 1 is colliding with cube 2. But how are we going to do that? We're first going to get a few axes based on the normals of the edges of the cubes. We're going to do this step by step, so we're starting with the axes of cube 1. These axes are displayed in lilac. As a quick note, SAT only gives accurate results if both shapes are convex. Then we'll need the positions of the corners. These will be displayed with red circles. Since the axes are vectors and the positions of the corners too, we can use the dot product to calculate the projection of the corners onto the axes. Then, by getting the lowest and the highest value on each axis, we can calculate the projection of the cube onto the axis. The projection of the cube will be displayed with the red bar. Then, we're going to do the same with the other axis. Then we're not there yet. We also have to project the other cube onto the axes. Since we're using the corners, we can calculate the projection of rotated cubes too. In order for there to be collision, the projections of both cubes need to intersect on both axes, which, right now, is the case. But that's not right. You can clearly see that the cubes are not colliding. There's definitely room between them. In order to solve that, we have to do the same that we just did with the axes of the second cube. Since we already did the calculations, I'm going to do it fairly quickly. These axes are going to be displayed in green. Now you can see the two of the projections are not intersecting, which means that there's no collision. Thanks for watching.
So quickly, to just sort of use this visual, right? You can see how one object has been projected into its own thing. In other frames of reference, they are overlapping, but in a particular axis, you have a gap. In fact, on the x and on the other x of 2, they are overlapping, just like we saw in one of our other examples with Steve and the crawler, but the creeper. But in the y of 2, there's a little gap there, and that gap means that there's a little line that you could draw perpendicular to that axis. Again, where I always got caught up. That would allow you to draw a thing or a ray or make a plane that is, the normal of the plane is that particular axis. That would allow you to, there is a place, there is a gap of some kind where the two are not touching anymore. So pretty eloquent little algorithm. There are other algorithms that can detect collision. One of the more famous ones. Let me talk about this at the end, actually. Another fun one. This is in the lectures as well, if you want to check it out. So there are a few other algorithms that can be used for collision detection. Generally speaking, the more advanced algorithms are used for arbitrary mesh collisions. For example, GJK or Gilbert, Johnson, and K, I forget the K stands for, very, very powerful algorithm using the Minkowski sum, which is a really cool little algorithm. It kind of determines, using the Minkowski sum of two objects, whether or not they're colliding by figuring out if the origin is in the sum of the set of the points. So it's kind of like this wacky linear algebra math thing where you take all the points, treat it as a set, take all the other points, treat it as another set, combine them, Minkowski sum in other words, and then if the origin happens to be inside of that sum, then you've got a collision. Very eloquent algorithm, and works not just for spheres and squares and rectangles, but for arbitrary mesh things. Unfortunately, it's not very good at determining where it's collided, and that's a real problem where it usually gets used with what's called the expanding polytope algorithm. But also there's another algorithm which I know very little about, given GJK's popularity, called VClip, which was developed by Mitsubishi, of all people, and I think they patented it because you'll find that collision detection algorithms are really, really important for robotics and manufacturing and things where you're taking a robot and coming into contact with another, maybe a robot or material, and you don't want to destroy the world when you do that. So a lot of work is done for this, involving like the combination of inverse kinematics and collision detection and so on. A lot of that comes actually from the robotics world and the manufacturing automotive world, or aerospace as well. So yeah, really fun subject, and hope you guys really enjoy it. I definitely do.